pleasure to welcome Dr. Boaz to Lewis University, a member of the Associated Colleges of the Chicagoland area or the ACA Consortia. Dr. Boaz is now currently at North Central College, where he's an associate professor of chemistry. A little bit of background: Dr. Boaz obtained his BS in chemistry from Lebanon Valley College in Pennsylvania. So he is an exposure in 2010, where he did some work on Fmoc-protected amino acid type stuff. From there, he moved to a university in New Jersey that some people may have heard of, being a Clarkson fan. I know Princeton is in New Jersey, so I never really bad thing about it. At Princeton University, where he did work on Dr. Gross, doing a bunch of metal-catalyzed functionalization, which you'll probably hear a little bit about CX formation today. From there, he moved on to here in Illinois, to North Central College, and then North Central College he teaches general chemistry, organic chemistry, and the laws of spectroscopy and organometallic chemistry courses. I'm going to let him tell you about what he does, but we're really happy to have you here. Thanks so much, and look forward to talking to you. So, Dr. Boaz.
Oh, thanks so much, Jason. So as Dr. Kelleher mentioned, I'm Nick. I teach at North Central College, specializing in all things carbon, because carbon is awesome. And I'd like to talk to you today about a little bit of work that my lab group has done in trying to develop new ways of making carbon heteroatom, so I'm just abbreviating heteroatom here with X, bonds, specifically from CH bonds. Okay, let's talk a little bit about this. So I'm going to do this talk a little bit backwards. I've seen this done a few times, and I kind of like this. Before I even tell you a little bit about what I'm doing, I want to actually show you the people who've actually done the work. Being a PI means that I sit, I write, I think a lot, but there are a lot of extremely talented scientists who are the ones in the lab doing a lot of really cool research. And so I've been really blessed over the past 6-7 years to have really great research students. And so the work you're going to be hearing about today comes from about 5 students here. And so I'll introduce you. So one of the first projects is based on benzylic oxidation. That was done by Ozma, Linda, Kelsey, and Haley. And then the second project, which is a little bit more preliminary, but a little bit out there, which I kind of like, is done by Emma Marcoon, who's right there. Fun story. The last conference that my lab was actually at in person was right here at the Iota Sigma Pi conference back in 2020 before the world caught on fire. We went to this conference, and then like 3 days later, our school was telling us, you got to go home. So it's kind of nice for the first conference back sort of is at the same place. We've had a lot of other talented students up here who I've posted. While I'm not going to be talking about their work, they've been working in areas such as ionic liquid synthesis and developing new labs for North Central and hoping to come up with better ways of teaching chemistry to college students. So this work here was funded by 2 parts. First, I'll thank the North Central College Faculty Development Fund, which funded a lot of the work on the second project. And then a portion of the first project I'll talk about, this benzylic oxidation, was funded by Eli Lilly. Okay, so let's talk. So overarching, looking at this in an overarching view, my lab group is interested in taking CH bonds, and so I've drawn just a very generic carbon-hydrogen bond sticking off a hydrocarbon there. And I am interested in replacing that carbon-hydrogen bond with a carbon-heteroatom bond. I'm particularly interested in making carbon-nitrogen and carbon-oxygen bonds simply because of their ubiquity in molecules of biological importance. So essentially, carbon, nitrogen, carbon, oxygen are everywhere in the molecules that help us do cool things for medicine, for health, and biology. So there are a lot of ways in which to make carbon, nitrogen, and carbon, oxygen bonds so far. And you guys have probably learned a lot of these in organic chemistry. So who here has taken organic chemistry? Who here is taking organic chemistry right now? Ah, awesome. So do you guys remember SN2? I see a few people shuddering. Okay, sorry. There are things like SN2 chemistry There are things like addition to a double bond. There are reactions such as nucleophilic acyl substitution. All of these create carbon heteroatom bonds, a lot of times of the flavor of carbon nitrogen and carbon oxygen. One thing that those reactions have in common, though, is that they're bringing 2 electrons to the party. When you draw an arrow in order to show the movement of electrons in a reaction like an SN2 reaction, the arrow has 2 barbs on it, right? Meaning that there are 2 electrons being transferred at once in that mechanism. It turns out, though, that it doesn't always have to be that way. You can actually have electrons move one at a time. And in doing so, you create these really nifty species called radicals. And in this case, you create a species that is a radical, which just means it has an unpaired electron on it directly on a carbon. Oftentimes, you'll hear these referred to in the context of oxygen. Has anybody heard of reactive oxygen species? So from talking with you guys about your research, you guys do a lot about that here. This is very similar. The only difference is that we're talking about this radical centered at carbon, not at oxygen. And so in 2 different ways, we have 2 strategies here. My group is seeking to create a carbon heteroatom bond from an intermediate radical that looks like this. And we can envision this happening really in a stepwise or concerted method. In the concerted method, we can imagine adding some sort of trap here, which is just going to link up with that radical and create our new carbon heteroatom bond, giving us an amine or an alcohol, ester, ether, things like that. Seems great, right? Well, the problem there is, what do you add to that that's going to trap a radical at nitrogen or oxygen? Yeah. So keeping that in the back of our mind, a second stepwise strategy, we can trap an intermediate with a well-known radical trap. So something like bromine, something like iodine, something like chlorine, something that's really well known to react with radicals, create a carbon halogen bond. From there, it's just good old-fashioned SN2 chemistry to basically boink off that halogen and create our functionalized species of interest. And so today, I'm going to talk to you about 2 different projects which attempt to use the stepwise and the concerted method of radical trapping to create new carbon heteroatom bonds. So let's take a little bit of a closer look into this. But before we do, we'll then start, after that, we'll go ahead and talk a little bit about radicals. So these 2 projects here involve the taking of a CH bond and replacing this with either with an oxygen or a nitrogen. And so on the top project here, what we've managed to do is take a look at CH bonds that are adjacent to a benzene ring. These are called benzylic CH bonds. Rip off that H dot, so hydrogen atom, and replace that net with an oxygen as an acetate ester. So we were able to do this in moderate to good yield, so ranging up to 86%. We've got 14 different examples of this working, and really kind of a nifty feature of this reaction, it is specific to secondary benzylic CH bonds. And what this means is if I throw a molecule with a primary CH bond in, it doesn't really want to work. I have to really push it in order to get reactivity. Also, tertiary CH bonds don't really react at all. And we'll talk a little bit more about that. So the second project that I'm going to talk to you about today involves trapping radicals directly at nitrogen in the hope of forming a compound referred to as a hydroxamic acid. And all a hydroxamic acid is it's like a carboxylic acid where you insert extra nitrogen in there. So in this case, we take an aldehyde, which actually has a relatively weak CH bond. We're talking on the order of 80 to 90 kilocalories per mole, so breakable. And treating this with kind of a funny-looking nitrate ester molecule, which is widely used actually as an antidote to cyanide poisoning, in a radical mechanism where we heat this pretty hot, generate the conjugate base of our hydroxamic acid, and then we can liberate that with a little bit of hydrochloric acid. And we'll talk a little bit more about that in a second. Before we really dive into this, however, let's talk about radicals. So who here knows what a radical is? Can you help me out? Just yell it out. I'll be honest, guys, I'm a scientist. I do awkward really well. Huh? Anybody? Just yell it out. There's no wrong answers.
A single electron.
Yeah. So basically, everything wants to have paired electrons. And we're going to tell you that in this case, it's not paired. It's got an odd number of electrons. This can be a single number of electrons, or in the case of carbon, it can be 7 electrons. We usually draw it as just a dot, so CH3 dot there, with the understanding that the rest of the electrons are in bonds. Sometimes we'll just ignore the other electrons. Really, the key feature is that we've got 1 electron that's not paired. So these are high energy intermediates. Carbon, and really atoms in general, really like to have paired electrons. They love it when all of their orbitals are filled, and they're filled with an electron going up and an electron going down. Actually, we were just talking about that, so this is great. And so these are actually electron poor. Carbon and a lot of these first row elements, they really want 8 electrons. Anybody know what that's called, wanting 8 electrons? Starts with an O, means 8. The octet rule, you betcha. And so having 7 electrons, they are electron poor, although from formal charge, they're neutral. So even though they're really not having as many electrons as we want, the bookkeeping tells us that these don't have a charge. And really cool thing here is that stability generally correlates with the same types of stability that you see with carbocations. So we know that a tertiary carbocation is more stable than a primary carbocation. It turns out the same thing with radicals. Tertiary radicals are more stable than a primary radical. So what I'm interested in doing is making these reactive intermediates directly from hydrocarbons. It turns out this takes a lot of energy. And the reason it takes a lot of energy is that this is a strong bond. So to break a strong bond, you've got to put in a lot of energy to make it break. It's sort of like breaking a rubber band, right? So in order to break a rubber band, you guys could take it, stretch it, and have it snap pretty easily, right? That's because its bond strength is not so strong. What if I replaced a rubber band with a bungee cord that you would use to keep something strapped to your truck? Same idea, right? Made out of rubber, it's stretchy. How hard is that to take like this and go break? Hard. And the reason it's harder to do that and to form those broken pieces is because your force constant is bigger. And in this case, your delta H, so your enthalpy, is really much higher. And so this is about 105 kcals per mole. So radicals are hard to form, but the reason we're interested in them is that they have really interesting reactivity and allows us to do things that, quite frankly, we just can't do with 2-electron chemistry. Okay. So the first problem my lab was interested in looking at was selective benzylic oxidation. There was a couple reasons we were interested in looking at this. First of all, benzylic CH bonds tend to be relatively weak. So methane, really strong CH bond, 105 kcals per mole. Benzylic CH bond is something like ethyl benzene. You're looking at about 88 kilocalories per mole. Doable, whereas methane, really hard. So textbook, you guys can tell me this. We can take a benzylic CH bond and we can transform that into a carboxylic acid by heating this with an incredibly strong oxidant, something like chromic acid, or potassium permanganate with an acidic workup. This will blow apart any carbon-carbon aliphatic single bonds that are attached to that, over-oxidize, so basically go further than we want to, and create our carboxylic acid. What your book doesn't tell you, though, is that this reaction is messy. Has anybody ever done one of these preparatively? Like, let's say you want to make 20 grams of the carboxylic acid. I have. It's a mess. We use the permanganate method. And so not only are you only getting about 40% yield on a good day, you've got to separate all of the carboxylic acid, which can be water soluble, from manganese dioxide, which is for all intents and purposes mud. So not great. So this indicates that there's some type of really cool opportunity here. We can create something that's going to be useful that can also help us make new products in a more efficient way. So people have looked at this for a while. So Amoco, which is part of BP Amoco, looked at making something called terephthalic acid. You guys are probably familiar with that if you have a water bottle. Many of you do in front of you. They're made out of something called PET, or polyethylene terephthalate. So it's basically a monomer of your polymer. They create this by oxidizing paraxylene with a cobalt manganese halide catalyst over oxygen. Heat this to about 500 degrees, pressurize it, boom, out pops terephthalic acid. Additionally, though, you notice that we're not adding just one oxygen to this carbon, right? We're adding 3. Oh, in this case, 2. 2 times 2 is 4. Again, don't ask an organic chemist to do math. So we have this problem of overoxidation. So what if I only want to add 1 oxygen single bond? So people started to look at this. In 2001, Phil Barron, in one of his really earliest works, showed that you can take IBX, or iodoxybenzoic acid, which is just an iodine with a very high oxidation state, and you can treat a basically aliphatic carbon chain off of a benzene ring with multiple equivalents and end up with the ketone. Step in the right direction. We're only adding 1 oxygen, but we're adding 2 bonds to that oxygen. So this is a net 4 electron process. So more recently, in 2011, there's this polycomponent reaction where we're taking propylbenzene, iodobenzene diacetate, so that hypervalent iodine species similar to Phil Barron there, adding in some iodine for good measure, tosylamide, which tends to be an oxygen transfer here, and heating this in dichloroethane. I don't tell you for how long, but this was actually a 24-hour reaction. You can get this to pop out. So we're taking 1 CH bond and removing that and creating 1 carbon-oxygen bond in about 48% yield. And so I talked to my group. I'm like, you know what? We can do this better. So ultimately, what we're trying to do here is create a system where we take off exactly 1 CH bond and replace that with 1 carbon-oxygen bond. You'll see that I have the O bound to Y, and you're thinking, well, wait a minute. Why is he making yttrium complexes? I'm not, I promise. That just can signify some sort of protecting group. But I'm being very specifically vague about this at this point because we didn't know. We're probably going to have to protect it to keep it from reacting more, but we don't know what it will look like. We want this to be catalyzed, because otherwise we don't want to have to heat this to 500 degrees like the Amico process. The catalyst and oxidant, so what's going to be the electron acceptor, have to be cheap, or else nobody's going to care. And then finally, we're probably going to need to protect any alcohols that we form, because alcohols, specifically benzylic alcohols, are very reactive. They're going to want to do all sorts of fun stuff afterwards, and all of those processes we don't want to happen. OK, so we took to inspiration. So the inspiration we took was actually some work I had done in collaboration with the University of Virginia looking at methane oxidation. So we were taking waste methane from landfills and leaky oil wells and figuring out a way to transform this into a liquid fuel, methyl trifluoroacetate here. And so we had found that simple KCl, so potassium chloride, sodium chloride works as well, solubility is not quite as great, and ammonium iodate and trifluoroacetic acid at relatively high temperatures will produce our methyl trifluoroacetate in multimolar quantities. And so this works actually pretty well. We figured out that this happens by taking a chloride catalyst, oxidizing this up to the halogen. Light or heat then causes the scission or breaking of a CH bond into a radical. This radical takes off H dot, so hydrogen atom, from a carbon-containing species, creating HCl. This carbon-containing species then reacts with iodine to create a carbon-iodine species. From there, it's just SN2 to wind up giving us our overall protected trifluoroacetate ester. And this worked pretty well. We were able to publish some cool papers about this. We got a patent on it. But this process worked really well for methane, ethane, and propane, and that was it. You added more complex molecules, crazy stuff happened, you get crazy amounts of intractable product. But we thought, you know what the promise is here? This works well, everything is super cheap, with the exception of the solvent here. Perhaps we could use this to solve our problem. And so we took a look at this. So my lab group said, OK, we need a simple benzylic CH bond. We have a whole bottle of toluene. Great. We'll take that, essentially mimic the exact conditions we did with methane. And it turns out we don't get any of the product that we want. Again, we're looking to make a carbon-oxygen bond off of the methyl group. And essentially what we saw was electrophilic aromatic halogenation. You guys remember that from organic? Usually the way you do that is you take a halogen, Lewis acid, heat it up, and you can get carbon-halogen bond formation. And that's all that's happening here. And in fact, one of the keys and clues that this is happening is that we're actually creating halogen in situ. So went ahead, ran this reaction, took a look at the UV vis because it winds up being sort of deep purple here. And we can see that what we wind up having produced is a little bit of iodine monochloride, so ICl, the inner halogen, iodine trichloride, and in this case, chlorine. So it doesn't necessarily work well. So chloride catalysts, not great. So can we change our catalyst, though, that will allow us to keep the right selectivity? So we moved on to something called an N-oxyl radical. These are plastics-derived catalysts, so they're super cheap, they're byproducts, and when you oxidize them, they can behave like a halide. They can abstract a hydrogen atom, and from there, they can go ahead and create the radicals that you're interested in. So the idea would be iodine 5, which is our iodate here, can do a 1-electron oxidation of our catalyst, called NHPI, N-hydroxythalimide, to form a radical, O dot. This 7-electron species here doesn't want to be 7 electrons. And remember, radicals tend to have similar stability as cations, right? How stable would something be if I told you it had a positive charge on an oxygen? I heard some chuckles. Oxygen's pretty electronegative, right? So it's not. It's like, yeah, I don't want this. Sorry. So you see that hydrogen there? It would be a shame if somebody were to come along and take it and an electron with it. Mine. And it does that. And it creates this carbon-based radical. So from there, could we somehow then trap that to form our acetate like we showed in our methane work? And so we gave this a whirl. So what we did was we took butylbenzene, we treated this with a 10 mole percent loading of our catalyst, which is some of these N-oxyl catalysts that we synthesized here. We took ammonium iodate, which is our electron acceptor, acetic acid, and heated this to 150 degrees for an hour. And lo and behold, the acetate ester popped out. So our best catalyst here was the plain Jane NHPI, so N-hydroxythalimide, and we were able to produce our butylbenzene acetate ester in about 86% yield. So no matter how we modified our catalyst, we essentially wound up with a lower yield. And this was just sheer luck that we picked a good one to start. We kept modifying. I was like, we can't have really hit the jackpot the first time around. It doesn't work like that, guys. But it did. And so this was a proof of concept. This is going to work. We're going to figure this out. So, OK, with that in mind, what do we want as our electron acceptor? So we started with ammonium iodate. And I'm like, OK, guys, every hypervalent iodine salt you can find in the lab, I need you to test. And we're going to find the one that works the best. Again, we started out with ammonium iodate. What do you notice? It works the best. And so I questioned my students, are you sure? It doesn't work like this. You never pick the best one out to start. You don't get lucky, but until you do. So ammonium iodate here wound up giving us the best yield, so it's an iodine 5 complex. Additionally, it just turned out that using stoichiometric amounts of this, so one equivalent relative to our one equivalent of substrate, gave us the best yield. So we managed to get lucky sort of 2 times around. OK, so now I say to my students, what else can this work on? So I want you to find every chemical in the laboratory that has a benzylic CH bond. We'll start with secondary because this is what this has. And figure out how well this oxidizes it to form our benzylic acetate. So they go into the laboratory, and they find that by and large, this works for most simple molecules that have secondary benzylic CH bonds. So it's tolerant of halogens. It can be tolerant of additional rings. You can actually make this work in, work for heterocycles, and it actually works fairly well. Ironically enough, though, our best substrate was our butylbenzene, which we started with again. So again, every once in a while, you do get lucky. But what this showed us is that this, while it doesn't have amazing substrate stability, so if you put things in like a thiol or put things in like an alkene, it will react and oxidize it. For simple molecules, this does a good job of taking a benzylic CH bond and replacing that with an acetate ester. Cool. So with this in hand, we like what we're doing. There are other types of benzylic CH bonds available. So can anybody explain to me what the difference between a primary, secondary, and tertiary CH bond is? Do we learn that? OK. Does it have to do with how many carbons are bound? Yeah. So a secondary CH bond will have 2 carbons bound to the carbon that is bearing the CH bond. That worked really well. So you can also have primary or tertiary benzylic CH bonds. So interestingly enough, this is not a happy camper. We struggled with finding substrates that would react under our conditions, even though they worked really well for secondary benzylic CH bonds. And it was a little bit of a head scratcher. But we told ourselves, OK, primary benzylic radicals, like primary benzylic carbocations, are less stable than secondary benzylic radicals because of hyperconjugation. So maybe that stability makes all the difference. OK, with that in mind, tertiary benzylic CH bonds should work better because they're weaker. So I said, OK, find tertiary CH bonds and let it rip, guys. It turns out they don't work at all. So this is really in contrast to what we see in the literature. So there's a ChemCom article from 2018 that shows this tertiary benzyl ether here. Using an incredibly similar reaction setup, will selectively only go after the tertiary CH bond. Down here, very similar reaction setup. So they're using iodine, nitric acid, which when combined together will make iodate, and a cobalt catalyst. They're able to selectively oxidize that primary CH bond. But in our case, this doesn't want to work well. And when given the option between primary and tertiary and secondary CH bonds, you'll only oxidize the secondary. Exactly why this is, we're not entirely sure at this point. We guess for the primary CH bond, it's too strong. The tertiary CH bond, our only guess is that it needs to get close enough to a reductant in order to react. And that might be tough when our reductant is iodine-based. But we don't really have a complete concrete idea of what's going on. So one thing that's really important with organic chemistry, and some people will argue with me, is this, is it's not good enough to just make something. You got to figure out how it's happening. Otherwise, you haven't really learned anything. And so we came up with an idea of what we thought was going on. Based on previous research and other literature articles, we thought, OK, our catalyst here is going to be oxidized by 1 electron by our strong iodine 5 oxidant, which is probably then going to create some sort of iodine 4 species in solution. Iodine 4, not terribly stable, so it's not going to stick around a whole long time for us to figure out what it is. This radical then, odd number of electrons, will take H dot from our secondary benzylic CH bond to create a carbon-based radical and regenerate our catalyst here. One thing we've noticed in our reactions is if we run them long enough, they get really dark purple in color, and we can isolate brown crystals from them. These brown crystals are iodine. So what we think is happening is that any radicals that we form are trapped in situ by iodine that's made from the reduction of iodate. From there, we create I dot, which is able to float away. It's actually fairly stable, and create a benzylic carbon-iodine bond. At that point, what we're able to do is simply do substitution chemistry to create our carbon-oxygen bond. So you can see we think we're going by this stepwise process. Create a radical, trap it with a well-known radical trap, in this case iodine, and then from there, go ahead and displace that iodine to create a new carbon-oxygen bond. So this is all well and good. Do we have any evidence to back this up? And that's what I told my students, figure it out. So they wanted to go ahead and take a look at this in 2 steps. First of all, they said, OK, we're going to need to figure out, are we actually trapping a radical with respect with iodine? So what my student did, her name is Kelsey, she synthesized this. Everybody has a chair, everybody's happy, right? So in order to kick off the game, you got to pull an electron off. You got to pull off the proverbial musical chair. That's where the initiator is from. So in the game of musical chair, the initiator is the adult who steals one of the chairs. It makes the children fight it out for a place to sit. When you sort of think about it, musical chairs is kind of a crazy game for kids to play. OK, from there, we could create this high energy intermediate. It turns out measuring a high energy intermediate is kind of tough. So let's make our lives easy and say we'll react this high energy intermediate with an alcohol so that we could create an easy to measure ester. So the idea would be we'd measure the ester and from there back calculate out about how much of this are we making. Easy way to start. So she combined these together. She chose acetonitrile as her solvent, AIBN as a radical initiator. AIBN just stands for azobis isobutylnitrile. It's essentially a solid that when you heat up, it just sprouts off radicals, gets everything going. She used N-propanol to make the ester. We added acetonitrile, and then we heated this in the chemical microwave. And lo and behold, in 35% yield, we're popping out propyl heptanoate reproducibly. OK, this is good. So I told Emma, we need a higher yield. So she's like, OK, I can figure this out. So she went ahead and screened a variety of different solvents to see could she push this yield higher. So remember, we're looking to make propyl heptanoate as a way of informing how much of this high energy intermediate are we making. Because remember, this will do nucleophilic acyl substitution, just create easy, stable ester. That actually smells quite nice. So what she found is that a lot of solvents work OK. Acetonitrile, 35%, dichloromethane, 12, THF, 11. Then she tried dimethyl carbonate, which we just had sitting in a bottle, and it worked pretty well. 50%, this is good. Dimethyl carbonate looks like this. The reason we had that around is we were trying to make it more efficiently for use in batteries. So give it a try. Worked. She looked at that and said, OK, what functional group is in abundance in that molecule? Starts with an E. Anybody got? Ester. Okay, let's find every ester we have and give it a try. So she tried ethyl acetate, methyl acetate, butyl acetate, and eventually she tried hexyl acetate, but she had to synthesize it first. And we found that esters not only work very well, you can tune the hydrophobicity of the ester. And in this case, butyl acetate works really, really well. We're reproducibly able to make this ester in 70% yield using a radical pathway. Cool. So at this point, all we've really done, though, is said, OK, I've taken an aldehyde and made an ester. Nothing is really said about carbon-nitrogen bond formation. So we need to prove to ourselves that we are making this nitrogen-carbon intermediate halfway through a reaction. The way in which we do that, getting ahead of myself. She also wound up screening alkyl nitrites. So she synthesized a series of alkyl nitrites ranging from hexyl nitrate, cyclohexyl nitrate, isoamyl nitrate. This is just isopentyl. Amyl's the old-fashioned name. And found that in this case, while other nitrites worked OK, our tertiary butyl alkyl nitrite was the best. So we then sought to figure out, are we actually making this carbon-nitrogen intermediate? And so one of the things we're interested in is creating hydroxamic acids. So we knew at some point we'd have to add a reductant into solution. We had a bunch of different reductants lined up, things ranging from dithionite to sodium triacetoxyborohydride, stuff that would not reduce the aldehyde, but would reduce an acyl nitrosyl. We found that zinc apparently seemed to work pretty well. The reason we tried zinc was we added the terbutyl nitrite, heated it up, nothing happened. We added the aldehyde, heated it up with zinc, nothing happened. So OK, the starting material is stable. Is our intermediate reactive to it? So she goes ahead, removes the alcohol, because we remember we're not trying to trap this anymore, and adds an equivalent of zinc dust. What pops out of solution is this white solid. So what we think is happening is that we're creating the zinc hydroxamate here, which is characteristically a white solid. So she took this solid, acidified it, took an NMR, and lo and behold, the 7-carbon tail of heptaldehyde, which is now our hydroxamic acid, is there. It matches authentically synthesized heptyl hydroxamic acid, which she made authentically from a different method. OK, we're good. So then finally, we looked back in the literature, and there's an old-fashioned way of testing hydroxamic acids. One of my colleagues, his name is Dave Rausch, would love this. He's a big proponent of qualitative analysis. And the way in which this works is you take a sample that you think contains a hydroxamic acid, you add ferric chloride and ethanol. This should form a bright red intermediate. She did this, it turned red. OK, I think we're in business. And so this is actually what happened yesterday. So she told me about this this week, and she sent me this picture yesterday. We're still working on what our yield is. It's a sort of a fluffy white powder. We don't know exactly how much of this is a zinc hydroxamate, but we're pretty sure that we are making this. But this is super preliminary. And this is really as far as the project has gone thus far. What we're looking to do in the future is A, really pin down that we're making this hydroxamic acid. B, got to up our yields. We want this to be preparatively scalable to create hydroxamic acids directly from aldehydes. Additionally, we want to see what kind of aldehydes can you use. Could you do this with benzaldehyde to create an aromatic hydroxamic acid? Or are you limited to aliphatic substrates? Or are you limited to zinc as your reducing agent? Kind of nifty if you could go ahead and create different hydroxamic acid salts depending upon your reducing agent. So things like iron, things like cobalt as powdered metal reductants. OK. So in summary, where we are in this project is that we've found that it is possible to oxidize an aldehyde directly to an ester in a one-pot reaction using alkyl nitrites as an oxidant, presumably through an acyl nitroso intermediate. And we've shown that this is able to happen in moderate yield. We're about 70%. very preliminary data at this point suggests that we're able to take a high-energy acyl nitroso intermediate and trap that by reducing it to the zinc hydroxamate in solution. And this is where we're working right now, but we're really optimistic that this is where this stands. Okay. And the nice thing about giving all of your introductions at the beginning is at this point, while this is all fresh in your mind, I'm more than willing to answer any questions that you got.
Questions from our speaker?
Oh, sure.
So a lot of those thermal.
Yeah. Mm-hmm.
Do you think under the catalysis?
Yes. Uh-huh. We think so. And so a lot of this really depends upon how those radicals are reacting. So what I've purposely skimmed over is that we think we're actually creating something that looks like this. So there's work in the literature that suggests that radicals don't just do a one-for-one replacement here, that they actually create kind of this nifty-looking intermediate called an oxyl-nitroxyl radical. It's got a lot of structural similarity to something called tempo. And so this is really going to depend whether it happens this or we simply have a bunch of radicals flying around and you're just pairing this with NO dot. That's really going to have an impact upon what our selectivity and sort of the regio and stereochemical selectivity of this reaction is going to be.
So it's like tempo to use for soft mediated so we could use them as terminators.
Certainly possible. Certainly possible. And so I think what's interesting is we've never tried to stop the reaction here. We've just sort of assumed that this is a hot reagent. Interestingly enough, though, we've been playing around with DFT. It converges there and stops. Yeah, it might not be as hot as we think. And we were thinking, OK, there are molecules out there that this is isoluble. We've never done it. But that's something that we're certainly thinking about, just because our ability to characterize an organic radical is limited. I don't have an EPR sitting around. But if you know someone who does, let me know. Mm-hmm.
Any other questions? Well, I appreciate you coming today. Thank you.
Of course.
For your time.
Mm-hmm.
And again, it was nice to have a tour through organic chemistry. So it showed you a little bit.
Absolutely. Sorry for making it involuntarily participatory.
Thank you, and hopefully we'll see you.
Absolutely. Thanks, everyone.